CAS is probably the most successful helioscope in the history of physics, searching for solar axions and other rare particles. And he's also involved in the DALI experiment that we have here at the IEC. Also, he's one of the pioneers in proposing alternatives and an isotropic distribution of dark matter. And I think this is the topic for today. So, Konstantin, go ahead.
Thank you. And how I can change the slides? Here.
No, I will change it.
I think where? In between, I thank Javier for the nice introduction. And from what you heard already, you will think I am solar physicist, because formally, since 26, 27 years, I look to the sun, okay? But this is misleading. I'm not solar physicist, and what I will present you today, it is a cross-disciplinary matter. And I tell you from my experience, cross-disciplinary sounds always good if you ask for funding somewhere, but to do cross-disciplinary something, you always have a problem, because at least one half of the matter, you have no idea almost. So it is dangerous. So today, I give here this talk with pleasure, just to cross-check myself, okay, of what I'm doing since almost 30 years. So just for your knowledge, I am an emeritus professor at the University of Patras. Emeritus means you have a contract which never ends, okay? So that's a good thing. But my professor in Germany, who got the Nobel Prize later, and I have heard him once talking about his situation, he said, as emeritus, you are a poor man. At that time, it was a joke. Now it is no more a joke. So on the left, you see a number of people with which I have collaborated and collaborating still on this matter. And one is also Javier, entered since some time. And we go to the next slide, which this is the title already has a correction. Overlooked dark matter signatures, but I refer only to streams. Only streams it can be overlooked. Not streams cannot have been overlooked. So in the next slide, you see a number of references, say, starting with Wolf 1859 and ending with the last paper we have uploaded number reference 11 1 week ago, the second version, which is much better than the first one because we got feedback and we improved things a lot. So this is a summary of what I will present today. And if someone wants, for some point, go deeper, you have a reference. You can click it, not only number. You can click on the web page and have it on the screen. Next slide, please. So if we talk about dark matter signatures, we can, or we must start with Zwicky, who discovered making cosmic observations, 1933. He had attention and observation where he saw something which does not fit to what people knew at that time and also today. Because if we look there today, we will end up with the same question, with the same contradiction or tension. So he observed something there. It was more mass than he expected, than people saw by, say, visible. And he defined this extra mass he needed as dunkle Materie in German, dark matter, everybody knows in between. So in solving a problem, not searching for something, he discovered such a thing like dark matter. So this is the discovery of dark matter. After that, in fact, we don't have something solid in hand about dark matter. Okay? So that's the interesting thing is now we say dark matter interacts gravitationally. And this is also misleading because we will see immediately. But if dark matter interacts a little bit more or somehow than by gravity, then we will have a big gain. So in this direction goes my work since 3 decades. Next slide. Oh, down there was something reminding me. Back, please. Yeah. The whole thing is, can we apply his reasoning of Zwicky also locally? Not only cosmic distances, but also here, local, around the Earth, inside the solar system, at the sun, and this is certainly locally. And next slide. So dark matter, you have always this pi, which is 27 dark matter, which is 5 times more than, you know all this. All that we know so far after so many years is that dark matter is very well hidden. It is hidden if you look at it as if it does it on purpose to hide, okay? And then in between, little by little, people came, I would say for outreach, to a conclusion that dark matter is something which does not interact. It does not absorb or reflect or emit electromagnetic radiation. But this is certainly wrong and certainly misleading, in particular for young people. You give them no chance to detect dark matter because it's hopeless, okay? While even who search for dark matter, who work in this field, we expect in the one or the other way to have an interaction with a dark matter which might have this or this property and to see it directly. So this is certainly misleading, okay? Unfortunately. So next slide. Yeah. So dark matter was originally, I don't know, until maybe 10, 20 years ago, rather 2011, 15 years ago, that it was, we thought it is something like a gas which is just around, okay? And then cosmologists, Fogelsberg and White, they make a paper. For some reason, I have a paper from 2014. The actual paper is of 2011. I could not find the last few days. And so around 2011, so people proposed that dark matter, based on cosmological reasoning, must exist also in form of streams. Streams is a particular state of matter because in the case of dark matter with velocity, as you know, 10 to the minus 3c, if streams come into the solar system, we don't look today beyond the solar system. They can undergo gravitational focusing by the solar system bodies, by all planets, including the moon towards the Earth. Okay? This is simple, and we have done a paper on this. We will see 2003 with 2 German colleagues from the CAS collaboration. And the one is a professor in Frankfurt, Jacobi, and the other is a male who's like me, but in China for the moment. So this fact that dark matter you can have in form also of streams and said by somebody else, not you say everything, then you arrive to a conspiracy theory, and then you are lost, okay? So that's why I like to implement and to utilize other people's work. we won't find dark matter. That's the first. Yeah. And so this is important. We go to the next. Yeah, and then there is another guy, Nobel 2004. This is Wilczek, a theoretician, a clever one. So he gave a seminar at CERN, and the title was something about LHC, and then most of the time I think he talked about actions and not so much about LHC. But with LHC, title of the noun, you get invited. So don't communicate this, please. So in the seminar, Wilczek say, you guys follow something which is unknown, which is anomalous, which is mysterious. That's where you have a chance to find something, okay? And this principle we apply here, although, to be honest, I have applied this principle to 1999 when I started with cast experiment at CERN. And so now we stay within the solar system, and indeed the solar system is full of mysteries, be it in the sun, which is many. I don't know what is not mysterious in the sun, and also here on the Earth, the outer Earth, the atmosphere, or even the inner Earth. We will see a few plots which we have made. And yeah, so we are eager to see it. We see something in the solar system as unexpected, unexplained, unpredictable. Then we look at, and what we do, I say that now free, it comes another place again, is the only thing we can look is whether we have some planetary dependence. This should be then, and is, an extra argument that what conventional physics, known physics, has called as a mystery, as anomaly, to see how it behaves, whether this shows also planetary dependence. Then you have another parameter which makes the mystery more mystery. So it may be you have then a chance if you go this way, that one day you arrive to some result better than we will see today, except the very last few sentences, which is in your topic. That's why also you will see I am glad to be here today. So, and then the alternative is dark matter. If you cannot explain something, you always can say this can be dark matter, but you don't convince people for a long time. But you can start with looking for planetary dependency, looking for gravitational lensing effects. It is a strong argument that what happens there in that effect, in that anomaly, has to do with streams. Most probably. Next, yeah, it's here. These slides took me a long time to prepare. And so the startup of this work is, let's say, Wilczek's proposal, doesn't matter, but local. And then we work in a way searching, single out enigmatic measurements. So they are candidates. For example, we want to see whether these enigmatic observations couple somehow to streaming dark matter. Then if you observe there something, then you discover or you work for dark matter properties or discovery, and even streams. Streams is a special, I wouldn't say quantum state, but there is a special state that it comes all the time. And I asked these two people, the first one is in between full professor in MIT, how long are these streams? The streams, the cosmic streams, have studied the cosmic time, of course. And then they travel all the time, it costs nothing. And then in between, they have been cutting in pieces. Tell me the astronomers, okay? And I asked him specially for our purpose, these streams, how long are they? 100 meters, 100,000, etc. And he told me 100 parsec. 100 parsec is infinite. And if you put it on the velocity of 10 to the minus 3, it lasts for years, forever, for your experiment, which we will consider here. And so this is this, and then dark matter streams have this special advantage that if they come into the solar system, indeed your solar system, then they can undergo. We have the sun, we have then moving around gravitational edges all the time. So if they come there, and occasionally they are aligned, the solar system body, you, the detector, and the incoming stream, then at the focal region, you have huge. Okay, if we are with huge, I mean more than 10 to the 10. And for a while, I did not use this number because I did not trust myself arriving to a number of 10 to the, I think 11, 10 to the 11 can even be the gravitational. So, and then we will see soon. There came two people, one in US, I think they were both astronomers, and one in Japanese. I was in contact with him too. And they talk about 10 to the 9, 10 to the 10 flux enhancement, which is enormous. If something you never have a chance to see, at that moment you have, okay? And and that it was in 1859 by Wolf, who wrote a nice, polite letter to the editor of the journal and saying, in my opinion, it could have to do this fact, this 11-year cycle and the 11.8 orbiting period of the Jupiter, they must have something to do with each other. A nice, polite. He could not give a mechanism. At that time, it was not in fashion of dark matter. Everything you don't understand is dark matter to first approximation, but it's not enough. But even you make this a step forward. And so, all in all here, we look for something unexpected, unexplained, unpredictable, and we want to detect also planetary dependence to have something solid in hand, so to say, that this what we observe might have to do with streams, dark matter. And what happens, let me say already now, yes?
Just to clarify, what is exactly the United's proposal?
Which proposal is, look, you guys look to something which is anomalous, enigmatic, mysterious, and look into this deeper. Mysterious means you don't know the physics behind. So look at there, you will discover something which you don't know so far. So it was a simple argument. I wasn't that's what I have written down from his whole speech. But when I invited him to come to the cast experiment, he did not have time. Doesn't matter. Okay. So, and then what happens, people at that time, today, speak about an extra planetary force must be at work, which does not exist. The only force we have is the very, very feeble gravitational tidal force of the planets or to another planet or even to the sun. But this force is extremely feeble. We will see soon. There must people the physics, solar physics paper I have seen, there is missing a factor of 10 to the 11. I mean, the extra force we can have on gravity, by gravity from the planet on the surface of the sun or so, it is 11 orders of magnitude smaller than the gravitational force there on the sun from the sun itself. So it cannot easily have an impact, except if it goes over giga years, etc. Okay, but here you see observations which happen, repeats every month or every year, etc. So next slide. So and then in between, after this very definition I gave to you about having dark matter, people start talking about dark matter at the end. It might not interact so terrible feebly, but it might interact a little bit more. And next slide, it was recently published in Astrophysical Journal. And you know, Astrophysical Journal is not an easy journal. I have done only one publication in my life in Astrophysical Journal. And he writes there, I cite, this proposal might overturn our usual assumption of extremely weak, feeble interaction between dark matter and the ordinary matter. So this was done a few months ago in this journal. Someone from Bucharest, Ionel Lazanu, sent me this information. Next, please. Yeah, this is an interesting story where I said, if you have something and you don't understand, dark matter, you certainly first step, and then we see. So they observed in the night Jupiter an irradiation, an excess irradiation in the infrared or far infrared. And this irradiation they had identified of some cations, we see in the next slide, of 3 hydrogen cations, 3 hydrogen cations. This, in their atomic or molecular transition, they give you some micron radiation, and that's why they have observed in the night of Jupiter in excess. And but the question is, what is its origin? So I like that somebody else thinks immediately, looks to dark matter as a candidate, and not leave it alive as something hopeless and don't talk about it. Next slide, Javier, please. Yes, and then all the other publication is practically is huge interest. There are two good physicists, Rebecca Lind and Yuri Smirnov. They have done also other papers, I saw only this one, where they say the picture we have for dark matter when they can be trapped by solar system bodies like the sun, the earth, etc. Is that they hit once the body, they interact somehow with a, even though we say they don't interact, they lose velocity in the scattering. It can be elastic. They lose velocity and they lose more and more, and then they come to a certain point where they are in the solar system body. They cannot escape anymore, and they are trapped there. They accumulate. And the idea, the picture so far was that the accumulation occurs in the center of the body, of the Earth, of the Sun, etc. So for certain cases, they calculated, for certain cases means for certain cross sections, for certain degrees of interaction, they calculate, they have plotted nice curves. I don't show here to make my talk not too long. They say that they can have accumulation where the dark matter density of the surface of the Earth is some 13, 14 orders of magnitude larger than the nominal value of the global, the universe, say, or mean value of dark matter of only half a hydrogen per cubic centimeter mass. Okay? So this is a very interesting information one could keep in mind working in this field. Next slide will bring me to planetary gravitational lensing. So the planetary, the gravitational lensing has to do usually with light which of course cannot penetrate any solar system body, but we have the gravitational energy outside. But you can have, and this has been said before, gravitational energy also from the inner mass distribution of some solar system body, the Earth, the Sun, etc. And here I give you a number. These are the two astronomers, Prezzo, 2015, and Sofu, 2020, where they say the inner mass distribution, we say the Earth only. As an example, you can have a gravitational lens performing there very well. And then you can have on the other side, if the stream aligns well with this mass distribution, to make it simple, I can tell you the stream must look to the center of the body, to the center of the Sun, to the center of the Earth. Then you are good aligned. So these people who focus better why to predict cosmologically the streams, they, what I want to say, I forgot it. It will come later. It will come later. So we stay here. So even the intrinsic Earth can bring you on the other side an amplification factor of the flux of 39. We share papers from earlier where we consider as given dark matter is a gas around us. So then the dark matter enhancement due to gravitational effects was at the level of percent, maximum 4 or 5%, which is nothing compared with the factor 10 to the 9 you can have with the intrinsic gravitational lens of the Earth. I'm talking now. Yeah? And yeah. So this is the paper we have done with these two Germans of cast in 2003 and also in 2014 after one solar cycle. And we point out that the gravitational lens, which is completely discouraging because you get into the focal length at 555, I think is the number, astronomical units. Hopeless to make here an experimental method. Okay, but because it goes with random velocities wherever, then with velocity standard line is 3c, you get an enhancement factor. I mean, you shorten the focal length by this factor square. Next slide. Interestingly, the new science, there was a cover page saying perhaps we are looking at the Sun with the wrong way. And with respect to the solar composition problem, there is a solar composition problem in astrophysics. Okay? We have the problem we look at, and we have evaluated, we have found planetary intelligence. So we have also this pointing to gravitation, to streaming gravitational effects, also for this problem. And we got the data from the person who published it. But she gave the data very good understanding. And the next slide brings us, then in short and faster, we were talking about the solar system, which we have the solar flares, mystery, solar corona, equally the mystery, the whole behavior of the solar corona and the transition of the chromosphere to corona. And then we have the ions here. We will see soon plots. And then in 1937, people have discovered there and called an anomaly. I'm surprised at that time, 20-25% effect. They said this is an anomaly. What was the accuracy? I don't know at that time. And then the solar metal composition I mentioned before, and the proxy of the solar activity, which is the 10.4, 10.5, what is it, centimeter line of the 2.8 gigahertz in any case. And all this, they reflect the solar activity. So we have too many anomalies where we add also this difficulty, so to say, of having also planetary dependence, and where it can bring us. Next slide, please. Okay. So here, yeah, here. Do I have a pointer here? Here. Very good. Here, and in order to plot of time, this is the black body radiation of the sun. Here at the top is 1 eV or half eV, 5 or so. And then when you plot the energy of the photons emitted by the sun, and this is the probability, you get such a distribution. You get a very nice, here is a logarithm, okay? You get a nice black body radiation, and about 20-30 eV, you don't follow the black body radiation. Then you have a huge excess. I mean, imagine here the coast, you are there, and black body should be somewhere there or there, don't know where exactly. So it is a huge excess, and this is a manifestation of the hot corona. I got this from who puts Axion, who invited Tino Axion to get with a collaboration with Atlas of the Atlas. The past experiment cannot do with Atlas. Fortunately or rather unfortunately. So this is a manifestation. And the question is, this was in 2002. And the question is, what is this? You must find out, come talk to me. And it took us, believe it or not, 15 years to look what is this from the point of view that it show a planetary plan. Yeah? It took 15 years, that's right. We did something else about it in between. And then the first approximation, you should never expect something random or something you don't understand, you cannot expect something specific. And then we got this distribution here. 1, 2, 3 cube peaks. Here, this height is 6%. 6% is the right number. We are not talking about promille effect or percent. And of course, you cannot predict this. This was measured. This was measured. So instead of only having the problem with solar corona of the temperature inversion, the most impressive thing I found when I started. And then if we have the temperature, as we will see, as a function of the radial distribution of the sun in its atmosphere, and the factor, last but not least, that the sun after 4 or 5 bigger years never arrived to thermodynamic equilibrium. Why not? And the only example we have to compare with is the Earth, not the Earth, the universe, when it was 250,000 years young. It had only the temperature of 3,000, 6,000 in astrophysics, as we say, factor 10 is nothing, okay? And there you got a perfect thermodynamic equilibrium, okay? Next slide. Yeah, you go with the back. Forget this here. So we have 1, 2, 3 anomalies of this region, and we add also the planetary relations. So the solar corona, the behavior, is 4 times or to the 4, maybe to upgrade a little the parameters. Next slide. Yeah. Again, this is our reference, and this time, 2017, we did wake up 50 years after in Australia published these measurements of the in black of the sunspot number as a function of the longitude of Mercury. Okay, this is not me. Alberto, not here. So you get yes, here. So this we have here, and he measured this. And if you read his paper, he was disappointed that we have observed such a thing. And I think I had the impression he thought he had something wrong to measure this, while the only force he had then and we have now and we know about is the gravitational tidal force. The gravitational tidal force of Mercury, here's Mercury, for the different distances, meaning for the different heliocentric longitude, has such the dust line, 1/R2. And the other two things cannot be explained. And he wrote immediately obvious that no simple theory will entirely account for this complex pattern. And he is right, of course, we too, because dark matter is anything else but the simple. Okay? And he concluded even, next slide please again, he concluded that forces of extrasolar origin can at least some influence along the reasoning of both property. But he said there, at that time, the word dark matter did not exist. Dark matter existed, but not the word. Okay? To say easily as the other colleagues that we don't understand this Jupiter night, it must be dark matter and the matter also. Next slide, please. The 11-year cycle, you know, is the biggest mystery of the solar system, and this, if you look to various things, almost ubiquitous. Next slide. Yeah, that's Wolf. About the solar cycle, he argued about the Jupiter being very near orbiting the periodicity of the 11-year cycle, and he suspected planetary influence in 1859. And this was the only remote gravitation force which was too feeble to be reasonable. I said before, which factor 10 to the 11. Next slide. And there, we are found 13, we did some papers there. And the first paper, we jumped into this business if you want, of the 11 years, and the title was the 11-year solar cycle as the manifestation of the dark universe. So we added the new figure, dark matter. And here you know that's the three peaks you see when you plot the reanalysis of sunspot number creation rate. Here is the period of Jupiter, and here the 11 years, and here the period of Jupiter and Saturn, 10 years. And the 11 years is the synod of Venus, Earth, and Jupiter. Some people add also Saturn, probably in some correction of what we said. Next slide. Yeah, this slide I got lots of slide sentence I got from a student of mine, which he became a professor before me. And so he told me from all this, the conclusion is something else must be there, which is not going on, which is not direct gravitational pull, and to explain this and this and this. So we must find some other interaction with dark matter, I would say the string dark matter also. And here we see usually for the N plus flares, 4 solar cycles, and next, we have projected here on the Earth longitude, the Venus longitude, and the Mercury longitude, the number of flares which we got from Astrofísica, which they not he polished them, he cleaned them, I think, compared to what we had before. And we got this distribution. When we see here peaking distribution. So peaking distribution has an advantage. They exclude remote forces. You cannot have a remote force 1, 2, or 10, or 5 astronomical units, and shows up only only during this 1 month or week. It is difficult, say, or impossible, not probable. And the next slide, on the left is the same as before. And here, the little story, we have 5 in this world about the physics of the dark universe. They're not easy to do. And we had the honor to have 4 referees. The 4th referee, he insisted until the end. And he came up where we thought it is done. He came up with a clever question. No, these are not pitch what you played there. These are just outliers of something at this level. So, my personal comment on this is I should have expected outliers from downwards. The outliers, you don't have a brain to go way upwards statistically. But this should not have been enough to print the paper. But the whole thing is to bring the paper through. And then, but before he came with these questions, we had to convince ourselves before we go out to a paper. And what we have done is we had this period was of 4 solar cycles. And then we had a reason, physics reason, to divide all these measurements, before the, yes, 5 minutes. Which number is it? 25. The catastrophe, but I will accelerate. Okay? Because I need to put the last 2 slides, or the last slide. We divide in 4, and we got 4 independent spectra for each solar cycle. And then we have multiplied each spectrum, 1, 2, 3, 4, bit by bit. And then, bit by bit, we came here to these huge peaks. So, by multiplying these 4, which is physics allowed, it was not a trick, it was not just random or only mathematics, but we got this, because if the referee was right, if he accepted this afterwards immediately, if this is a random number and these are outliers, if you multiply something which is random with something else and even 4 times, then the result should be something more random, not less random. And here you can see that this here goes down to 0 relative. This is certainly less random than this one. So then we convince the referee. Then go faster. The next slide I don't show is fine. This and the next slide also. Here only a comment. We see here the same flares projected on the longitude of Mercury, but in yellow is the product spectrum, and is also narrow. We investigate with a student right now to find out whether this narrow becoming line is a random effect or it has a physical reason. We will see. Next slide, please. Here, this is the extreme UV coming from the sun. Next, please. And this is the distribution of the other picture of the mysterious solar corona, where you have some step line going down, step line going up. But that's the discoverer. Next slide. This is the textile GPS, the plasma of the ionosphere. Next slide. And where people have discovered an anomaly in 1937. Next. Here we have plotted this total electric content, the plasma of the ionosphere, as a function of the Earth longitude. And this fact here, this region was 25% larger than this one, and this difference they got an anomaly already in 1937. We have plotted this here, one orbit of the moon around the Earth, and we subtract this from this, and then we got as a difference this one. And here, this is a factor of 6 between minimum and maximum. And for all measurements we have done so far, we never had such a difference about 6 sigma, if I'm not wrong. And the next slide. This is on the left, the original publication. Next, please. And then we have seen also for the plasma density planetary dependence, which is not evident. And the next, and then the next, very fast, we had taken earthquakes, and we have seen when the Korean analysis, we have seen a huge peak, relative huge peak, and the side periodicity of the motion of the orbit of the moon around the Earth, which indicates that the solar threads somehow couple to something remote outside the solar system. And it's nothing at 29.53 days, which is the sun-oriented orbit of the moon. And the next, and we will have played it soon. This is also the interesting thing. Read it, please. Next also. So the resume is for these two slides in a distance of 20 years that the ionosphere, the plasma we have in the ionosphere, does not reflect the variation of the solar activity while we believe, or you believe, that you teach us that everything of the solar atmosphere is dominated by the irradiation by the electricity by the sun. And the next slide. Here is a compliment for the theory paper about where you see the peak in the transition region of chromosphere and corona. And to my experience, this is the only measure that I have seen with a peak in the transition region. I must have seen 50 or 100 ideas explaining the solar corona problem. Next. This is with the upper stratosphere. We go to the next, we can get a look there, it's important. This and please, and next, again, here, I have this, the contact I have with him today, with Michael Penny, but we don't probably him, this is as independent astronomer. And when I explained to you all that, he gave that question, what's about if this is a planetary dependencies can happen or in the solar system. It's now some 4 or 5 years, we have not found appropriate data. But we say, we have a look into this, and we come down to the next slide. Go to the next picture, which are high energy. So let's say only on the left, which is a high energy positron with rigidity 1 to 2 gigawatt, which is equivalent, I have seen in the internet, in the Google, 1 to 2 GeV in energy. So these are positrons, super relativity. So, and then we observe planetary dependency, as we see the next last page, last slide. On the left, okay, you see here the mass longitude and the projection of the number of positrons, and you see such a distribution. You can say now this might be something random because the error bar we have there, I take the negative value, is wrong. Maybe also large. And then from this we went to this distribution when we had 5 orbits of Mars, one after the other. More we didn't have. For the 6, it was missing one bin, and we got a 0 there. it doesn't help you. And we arrive to the spectrum on the right. So again, apply the same logic. If this is junk, or if this is random, not physics, and you go from here to there by multiplying the way you get multiplied, by no means you can say this gives you an impression that this is something more random than this. I would say rather on the contrary, but certainly not that this is more random than this. And quantitatively, if you take this value or this value here, the maximum, and compare with the mean value of the other 9, it is not an outlier, statistical outlier at the level of 6, 7 sigma. This is a quantitative number because we have used raw data available with a bin of 27 days. We would have preferred if we had a bin of 1 day or 1 minute, but 1 day is a reasonable one. So this is our best result so far. It is the first one we have looked with data of people looking for dark matter. Okay, and this they were not for dark matter, but then they turned it to dark matter. And the next slide, I would like to thank you for this invitation. And let me, last but not least, stress that we are eager to data of high energy or very high energy cosmic rays to analyze in our way, and also do some other big works in the exoplanet time systems and get some data. It would be more than welcome to collaborate and discuss this. That's all I think I can say now. Stop here typing. Yes,
this microphone while I pass this along.
Yeah.
Okay, thank you, Kostas. Any questions or comments? Well, I can start by just one question. So you presented a lot of anomalies in the solar system. So in principle, one could argue that many of them or some of them could be explained by, being pessimistic, unknown conventional physics. Now you're taking the brave stance of, postulating that might some dark matter physics playing. So you show all this anomaly. So yeah, it's good. It's good. It's a very refreshing attitude. But did you explain what is the physical mechanism? What is the dark matter model that explains all this pathology? Because it's a complex phenomenology. How do you do it?
That's why I have shown fast because of the time. The time runs always against you. And as a research director at CERN told me once, we worked together with him, Bertolucci, the time is what it is. Okay, you cannot change it. From all these observations we have done, I find the model by Zwicky. Zwicky is a renowned theoretician. To make it simple, I don't think you will find an Axion paper which does not cite Zwicky. First, he's very good. I work with him. And from all what we have seen is that, as we have seen here, that his result, his simulation fits to the transition region chromosphere corona. Myself, if you have some other such distribution, I will be very interested for a future talk to show it. But really, the only plot I have found was this. The physical mechanism is the following. We have in physics many huge problems. One, the most, thick problem is why we have universe and we don't have anti-universe or anti-sun, anti-galaxy, etc. So he explains, his model was based on a reasoning to explain dark matter. But at the same time, it became a model of explaining also the charge asymmetry in the universe. So he has very he uses very different observations for his model. And his group, he has also solar physicists, okay? But all in all, this is my argument. His model fits to what we observe. It can be model. And what is his model in simple things? That cosmologically, in cosmic times, I think the temperature 40 keV or so, you create always matter and antimatter in physics 50-50, but then you create a state not like the WIMPs by the famous physicist Witten, but he creates a matter of antiquarks, and he puts inside 0.1 micron, 1 micron maximum, he puts 10 to the 25, he can put 10 to the 25 antiquarks. And this dust can have 1 gram, 10 grams, extreme case, 1 kilogram, but 10 gram is a nominal value. So this, they go through bodies and anywhere, and they have different effects. Even they have calculated, there were 3 people, him and other 2. The other 2 is Butker from Mainz University. The other is Flambaum, he's in Australia. All 3, they were working in the same lab in the ex-Soviet Union, and they came out. All 3 are good physicists. And they predicted that these things, if they come against the atmosphere, they will trigger some kind of, how to say, of oscillations, of not vibrations, as you have in when you get a modulation of density. And similar, you could say, I have a trigger, a potential trigger to trigger also a flare, not flare, an earthquake, which is just on the edge to get excited. And then he helps a little bit, and then you get it. I think this is the best model I can imagine, because the other from Witten, people search since decades, have found yet nothing, and I am surprised that people still insist searching for WIMPs dark matter. I may be wrong, and they may be right.
Okay, do we have any more questions? I don't see any, so let's thank Kostas again for his overview. Thank you.
Thank you very much for this opportunity. Good, great, yeah. And remember, next week we have partners workshop. When you write? When do you write? Around the 8th. Yeah.